Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be looking at a more general form of regular perturbation. So we are going to generalize our observation. So generalize, where we will look at asymptotic expansions of the form f is f naught plus f1 epsilon to the power f naught epsilon to the power alpha, f1 epsilon to the power beta, f2 epsilon to the power gamma, and so on so forth. Now important thing to note is where we have these powers are arranged in the ascending order. So each of the successive terms in this expansion of the function have lower, this is epsilon, have lower and lower orders of epsilon. Now these are not integers. These are not integers in general. So that is what we are assuming in this asymptotic expansion. So what we have is these are not positive integers. Okay. So which means that so the way it is set up is that limit epsilon tending to 0, epsilon to the power beta by epsilon to the power alpha is 0, right? So epsilon to the power beta is much less than epsilon to the power alpha, and that is what we have. Okay, so if this is the case where the next every successive terms are lower than the previous terms, then we have that this ratio is 0. Okay, so then the problem now is let us look at this idea through one example. So the example that we have is the following. We need to find the solution. So solve this problem: x cube minus epsilon e to the power minus x plus 8 is equal to 0. Now again we can try and do the same setup where we take all the terms that do not have epsilon on one side and all the terms having epsilon on the other side to figure out what is the solution. So notice that if we rewrite this, we are going to see that this is epsilon e to the power minus x. Now if we try and draw this figure, we will see that x cube plus 8 will have a curve of the form where the curve x cube plus 8, it is going to cut at x equal to 2, minus 2, right? And then e to the power minus x will be an exponential curve, so we have e to the power minus x. Now depending on epsilon, we will have a root which is the intersection of these two curves, so r1, and we only have one root as the diagram suggests, and r1 will be greater than minus 2 and most likely it is less than 0, so it is a negative root. Okay. So then what we have is we could possibly try and solve this problem using the method of regular perturbation. So we see that if we have that x is x naught plus epsilon x1 plus epsilon square x2 and so on so forth, and e to the power minus x is e to the power minus x naught plus epsilon x1 plus epsilon square x2 and so on so forth. So now we are trying our luck by using a regular power series expansion of the solution in the regular Taylor form. Now e to the power x will have this form, and we can see that this is also equal to e to the power minus x naught, which is a constant, times e to the power minus epsilon times x1 plus epsilon x2 and so on so forth. We can use this factor which contains an epsilon to be y. And now we have that this is e to the power minus x naught times e to the power y minus y, and where y is epsilon x1 plus epsilon square x2 and so on so forth. So this is much less than 1, right? And so what we have is that e to the power minus x comes out to be, again notice that if y is, again if we are going to expand e to the power minus y, so this is e to the power minus x naught times 1 minus y plus y square by 2 factorial minus y cube by 3 factorial and so on so forth. So this is my e to the power minus y, and then we have to start to plug what is y in each of these functions to see that we are going to get the following form. This is eventually, after plugging in the values of y, the series expansion, we see that this is e to the power minus x naught times 1 minus epsilon x1 plus and so on so forth, right? So we see that this is the case, and then our x cube on the right hand side, sorry, on the left hand side will be x naught cube plus 3 epsilon x naught square x1 and so on so forth. So we see that the following, that this is also equal to, well, so what have we got here? So x naught, well, we need to plug everything. X cube, we have this power series, we have the power series of e to the power minus x and so on. Let us plug everything and let us see what we get. We see that our net power series is of this form: x naught cube plus 3 epsilon x naught square x1 and minus epsilon e to the power minus x naught 1 minus epsilon x1 plus and so on plus 8. This is equal to 0, and then the order 1 term will come out to be x naught square plus 8. This is 0, and order epsilon term comes out to be 3 x naught square x1 minus e to the power minus x naught is equal to 0. Now from here, the order 0 epsilon to the power 0 term, we get that x naught is minus 2. So that is the solution we get, the real solution. And then if we plug this into our order epsilon case, we see that x1 comes out to be 1 by 3 x naught square e to the power minus x naught. So this is 1 by 12 e square. So up to 2-term expansion, we see that the solution x epsilon comes out to be minus 2 plus epsilon's, well, this is epsilon, well, no, not epsilon but e square, sorry. So minus 2 plus e square by 12 times epsilon, and plus order epsilon square terms, which we can continue to solve. Okay, so at least this is the 2-term expansion, the 2-term expansion. So we tried our luck using our regular Taylor series expansion, and our luck sustained, and we were able to at least find the regularly perturbed solution x of epsilon. Now can we extend our luck? That is, can we continue to solve this using these problems using the regular power series? Let us look at one more example. So I am not going to change the new example by much. So the next example that we have is now x cube minus epsilon e to the power minus x is 0. And the problem says we need to find find the two-term approximation. Two-term approximation to this problem. The problem now is that again, if we separate out all the terms containing 0 and all the terms, separate out all the terms containing epsilon and all the terms not containing epsilon, we will see that there is only one solution. There is only one solution, and that solution approaches 0 when x goes to 0 or epsilon goes to 0, right? So that only solution goes to 0, so it is nearby 0, and when epsilon goes to 0, that solution approaches to 0. So there is only one solution. Now the problem is that we will see that the direct Taylor series won't work. Won't work in this case because near x equal to 0, we have x e to the power minus x is 1 near x equal to 0, and x cube is epsilon, right? So near x equal to 0, the exponential factor is 1, and we get that x cube is now has been reduced to this equation, x cube is epsilon, or we see that x comes out to be cube root of epsilon, right? And we see that so what have we got? So this is so we were expecting a leading order solution here. So when we plugged in e to the power minus x to be 1 at the leading order, the leading order solution that we got, the x0 is coming out to be is on one end is coming out to be epsilon to the power 3, but the leading order solution should have been 0 because of this fact. When epsilon goes to 0, the solution should have been approaching 0. So we see that the leading order solution also contains epsilon to the power some non-integer, right? And so that is where our problems start, which means that our direct Taylor series method will run into these problems. Okay, so we have a contradiction here. Okay, so now we are going to assume a more general Taylor series expansion of this method. So let us assume that x is x naught e epsilon to the power alpha plus x1 epsilon to the power beta plus x2 epsilon to the power gamma, and so on and so forth, where alpha is less than beta is less than gamma, and this is the ordered pairing of the powers, and these are all positive, and xi's are not 0. Xi's are not 0. So what we have is that x cube, we start to plug in this new power series expansion where the powers are no longer integers. So if we start to do that, we will see that x cube is going to be x naught cube epsilon to the power 3 alpha plus 3 x naught square x1 epsilon to the power 2 alpha. We are just using the cube root formula, and so on and so forth. We will have higher order terms. So this is the two largest order terms in the expansion of x cube. And now so what we have is that since we have x is close to 0 in the leading order solution of this problem, we expect that e to the power minus x can be expanded about x equal to 0. So as follows, and so on. We see that this is 1 minus x naught e to the power alpha plus, and so on. And if we start to plug everything, we see that x naught cube e epsilon to the power 3 alpha plus 3 x naught square x1 epsilon to the power 2 alpha plus beta plus, and so on, minus epsilon epsilon times e to the power minus x. So this is the expansion of x cube, and now we are going to put in the expansion of of e to the power minus x. So this we have that 1 minus x naught e to the power epsilon to epsilon to the power alpha and then so on so forth, right? So we have, this is the expansion of our e to the power minus x using the power series expansion of x. Okay, so now this is set equal to 0. So now we have to solve this. Notice that we have, let me call these terms as 1, this term as 2, this term as 3, and this term as 4. All the other terms which are not written here are higher order than these 4 terms. So we only consider the lowest order terms of epsilon. So notice here that 3 epsilon will be certainly less than, 3 alpha is certainly less than 2 alpha plus beta, because alpha is less than beta, right? And we expect that the cube term must be remaining. So we have to retain this cube term, because otherwise if we take if we try to cancel off this cube term the cube term has the power of epsilon, which is most likely the lowest order. So now we could either so what we have is that we have to continue to find the final solution. We have to continue to find these powers alpha, these powers beta, and so on, right? So our first task at hand is to find alpha. What is this alpha, right? And we find it through balancing. We do that through balancing, right? So note that for all xi equal to 0, we have the LHS cannot be 0. Why? Because of term number 3. We have a term sitting epsilon, where for epsilon not equal to 0, the term number 3 will contribute to a non-zero term, and we will have the LHS to be non-zero. And we are equating a non-zero term to equal to 0, and that is not possible unless and until this term number 3 gets cancelled with some of the remaining terms. So we could possibly since we have that alpha is less than beta, we would try and balance term number 1 with term number 3. So we balance term 1, let us call this term 1 as T1, with term 3, because alpha is less than beta. So the order of term 1 is lower than the order of term 2, right? And so that is what we have. So if we do that, we have epsilon to the power 3 alpha is epsilon, or alpha comes out to be 1 over 3, and that is what the value of alpha is, right? And now if we do that, so what have we got? So then if we try and do that, let us so notice that since we have balanced term number 1 equal to term number 3, so our term balance the orders of term 1 and term 3, and that is what brings us to value of alpha. Now if we balance term 1 and equate it to term 3, we see that term 1, from here we are going to see that x naught epsilon to the power 3 alpha now becomes epsilon, and equate it equal to term 3, which is epsilon, or we get that x naught is equal to 1. From here we see that x naught is 1. So now we have not only found x naught, we have found the power of alpha as well, together with x naught. Now the next task is, the original problem said that we needed to find 2-term expansion. So the next task is we want to find what is this beta for the two-term expansion. Notice that in the original problem, we were trying to find the first term, which is f naught e to the power alpha. So we found x naught, we found alpha, and now we want to find f1 e to the power beta. Okay, so let us try and do that. So the second task is we find beta. And again, since x naught is not 0, we will have that. Let us try to see all the terms. X naught is not 0, and of course e to the power alpha, epsilon to the power alpha is also not 0. So term number 4 is not 0, right? So this means that the term 4 is not 0. If the term 4 is not 0, we see that we need to balance term number 4 equal to term number 2. So we balance term number 4 equal to term number 2, and because that is the highest order term which is remaining. The other two terms have already been balanced for finding alpha and x naught. So balance the order balance, and we see that so if we do that, we will see that we are going to get 2 alpha plus beta is equal to 1 plus alpha, or beta is equal to 2/3. Beta is equal to 2/3, right? From here we have plugged in, of course, we have plugged in alpha equal to 1/3, and that is going to bring us our solution. So beta is 2/3, and now if we are to solve, similarly equating term 2 equal to term 4. So now equating term 2 equal to term 4, each of the term now has order 2 alpha plus beta, which is order epsilon to the power 4/3. Beta is 2/3, alpha is 1/3, so 2 alpha plus beta is 4/3. So now we are equating the terms of order epsilon to the power 4/3. We see that we get the following equation: 3x naught square x1 plus x naught is equal to 0, or x1 comes out to be negative 1/3, right? Because x naught is 1 or x1 is negative 1/3, right? And so what we have is the two-term expansion now this time will be x epsilon is x naught is 1, and times epsilon to the power 1/3 minus x1 is 1/3 times epsilon to the power 2/3, and so on so forth. So using this, notice that using the generalized power series, that is where we have chosen epsilon to the power some non-integer numbers, we have been able to figure out the Taylor series expansion of the solution, right? We see that as epsilon goes to 0, our solution also goes to 0, and our expanded solution exhibits the correct characteristics for the limiting case. So that completes our discussion on finding the solution to the algebraic equations for using the regular perturbation methods. Now in the next module, I will be trying and sorting out how to use regular perturbation using regular perturbation in problems involving differential operators. And later on in more advanced problems, we will be using the so-called the singular perturbation methods, and we will be heavily using these term balancing that I have shown in this last example. So thank you so far for listening. Thanks a lot.